So this is this morning the third lecture. So classical numerical methods about and using forward-backward PDE system and forward-backward SDE system. As yesterday, please ask questions in the chat if you want. And also, I guess that there will be a break at around 11:30 this morning. So Mathieu, please, the floor is yours.
Well, thank you very much, François, for the introduction, and thanks again to the organizers for these doctoral lectures. So this is lecture number 3. We had 2 lectures yesterday. In the first lecture, I basically introduced the paradigm of mean field games and gave some motivations and some background information. In the second lecture, we discussed the linear quadratic case, which is a setting in which we don't really need PDEs or SDEs. We can reduce the solution of mean field games to ordinary differential equations. And I illustrated a few algorithms on ODE systems, forward-backward ODE systems. So what I would like to do today is to move on to more complicated settings beyond linear quadratic, because we cannot do everything with linear quadratic, and to obtain the PDE system and to say how we can solve this PDE system numerically using mostly 2 algorithms I will describe today among several possible methods. And then I will describe methods for the forward-backward SDE system, so based on the probabilistic approach to mean field games. So again, you can find the slides on my webpage, and you can also, based on the slides, download some codes that are provided just for the sake of illustration. I will describe that during the lecture. So I will start with an introduction just to recap the background information we need before discussing numerical methods for the PDE system. Then I will spend one section on optimization, which are also based on the PDE viewpoint, but they don't directly tackle the PDE system, but rather use a variational viewpoint on mean field games, and then we can, based on that, develop optimization techniques. And then section 4 is about MKV FBSDs. So what we've seen yesterday is that typically when we try to characterize the solution to a mean field game using optimality conditions, we obtain not just a backward equation as we would obtain in standard optimal control, but this backward equation is coupled with a forward equation, which describes the evolution of the state or the evolution of the population distribution. So whether we look at PDEs or SDEs, PDE approach or SDE approach, in any case, we end up with a forward-backward system, which is in general fully coupled. And we have to tackle this forward-backward structure, which is a challenge both for the theory and for the numerical aspects. So here we are going to start with the PDE approach. And when we try to design a numerical method, at least, let's say, using a classical or traditional numerical analysis viewpoint, we need 2 ingredients. One is a discretization, because we cannot put the PDE directly in the computer. So we need to discretize in some way the solution. And the second ingredient is a way to compute the solution to the discrete problem after we have discretized or approximated using some finite dimensional object. So I will distinguish the numerical scheme itself and the algorithm, and possibly for one numerical scheme, you can have multiple algorithms to solve the discrete systems that you obtain. I will focus on some methods, but you could explore other methods. So this was a PDE system that we had yesterday for mean field games. So again, H is the Hamiltonian, which is based on the running cost and the drift. And you see that you have a second-order term, second-order derivative. So this was a Hamiltonian, and here we have second-order derivative if there is noise in the dynamics. So this nu here is a notation for sigma squared over 2 when the dynamics was given by dxt equals b dt plus sigma dwt. So in some of the numerical methods I'm going to present next, we might be interested in the case where nu is equal to 0. So if you take nu is equal to 0, it means sigma equals to 0, which means you want to remove the noise and you are interested in so-called first order mean field game. First order in the sense there is no second order derivative, there is no Laplacian in the PDE. And this can be easier in some sense or more difficult because maybe the solution is less smooth and maybe you need specific numerical methods for that. In particular, the probabilistic approach is maybe not that well suited if there is no noise in the dynamics. So this might require specific methods. And more generally, very small diffusion is leads to solutions that are less smooth. So it could be challenging. So this is our PDE system. Let me stress again that we have a terminal condition. So little g was the terminal cost, and we have an initial condition here for m. And this is where we see the forward-backward structure. I cannot solve for m before finding gradient u, and I cannot find u before finding m. So I have to solve this forward-backward system at once somehow, or at least I have to solve the whole system. I cannot solve one PDE before the other. All right, so when we think about scheme, there are a few properties that we might want to preserve. I already mentioned yesterday that discretizing is not always so trivial. Of course, you can do it in a very simple way, but maybe you will lose a lot of properties. So what are the kind of properties we would like to save here, we would like to keep? Well, because M is supposed to be the distribution of the population, we probably want M to be non-negative, and we want M to have a total mass equal to 1 at each time step. Another properties that is going to be very important for us is that if you discretize and you take the mesh step, so we are going to make some steps. If the mesh step goes to 0, then the discrete solution, the solution to the discrete system, should converge in some sense to the continuous solution. Otherwise, we are solving a discrete system, but when I take a very fine mesh, it doesn't really represent the continuous solution. So there is no point. If the original problem is in continuous space and continuous time, you really want to approximate this solution. So you have to think carefully about the discretization. Then maybe a little bit more subtle. Here we have a very specific structure between the forward and the backward equation. And in fact, you can see that the KFP equation, so the forward equation, is the adjoint of the linearized AGB equation. So this is a property that I will come back to it later, that we would like to keep even in the discrete system, because it gives some nice properties after that, some nice consequences that you can deduce from this structure. And this is a kind of structure that we use when we study mean field games and existence, uniqueness, regularity of mean field games. So the last bullet point here is that in some cases, the PDE system can be interpreted as in a variational way, so as the optimality condition of continuous optimization problem, and we would like to keep that at the discrete level, and maybe even beyond the variational case. So all of that is just to say that we need a careful discretization. After we obtain a discretization, the next question is how can we solve the discrete system? And this will be the algorithmic part. So this section 2 is going to be about 2 numerical schemes. I will mention at the end that there are other possibilities, but for the sake of time, and also because I will present methods that I'm most familiar with, I will focus on these two methods and mention at the end other possible methods. So the first step here, I clearly distinguish, you see, a finite difference scheme and then algorithms for this finite difference scheme. So I will follow the scheme introduced by Ivajdu and Italo Caputo-Dosceta, and then reused and extended in several works. For simplicity, we are going to consider the domain to be the torus, and to simplify notation, I will take one-dimensional case, but you can extend to two-dimensional. So if you want, you can do this as an exercise, write the 2D version, and it is pretty similar, except you have one more index everywhere. Nu is equal to sigma square over 2, and we are going to take nh and nt steps respectively in space and time. So what does it mean? It means that my domain is something like this. I have 0, 1, so this will be the space for x, and the space for t is going to go up to time capital T. So I have a square or a rectangle. There is periodic boundary condition, meaning that I identify 0 and 1. So this will be convenient because we don't need to think about Dirichlet, Neumann, and other boundary conditions. But I will show some examples later with other boundary conditions. So you can extend the scheme and include boundary conditions. And then we say, well, we are going to make a grid like this. So I'm going to have a number of points, which is nh. So sorry, there are nh steps in space and nt steps in time. So I discretize like this, and you end up with a grid. And what we are going to do is we are going to say, well, I want to know the value of u and m at every point of the grid. All right. Here, 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 everywhere on the grid. And what we are hoping is that when the grid is finer and finer, we are approximating the continuous solution. So I will use the notation h for 1 over nh and the notation delta t for the time steps. And I will write th for the discretized torus. Remember that at time 0, so this is time 0, m0 is known. So here I know m0. And because we are on a grid, I will write rho 0I for I between 0 and nh. Okay, so in order to approximate the PDE, we are going to replace it by a finite difference equation. And this finite difference equation relies on finite difference operators. So we replace the time derivative by this derivative here, the Laplacian, the partial derivative in space. And you see at the end, probably the trickiest part is this gradient here. And I stress that it has two components. So this is because there are two ways to approximate the derivative at point I. So when you are at I or xi, let's say, you are here, you can look at xi plus 1, and you can look at xi minus 1, and you can use the value of u here to compute the gradient, or you can use this one to compute the gradient. So you have two ways to approximate the partial derivative. And in fact, it might be interesting to use one or the other, depending on how the solution is evolving. So that's why the gradient has two components here. And it is in dimension more generally, so you need more dimension than the space variable. So let me take a specific setting. So I'm going to consider that the drift is just alpha. So this means that the agent controls her velocity directly. And I am going to consider that the running cost, f, is separable in the sense that it has an additive dependence in alpha and m. So this simplifies many things. And I will, so here I will use the notation L for the function of alpha and the notation f0 for the function of m. If you look at the definition of the Hamiltonian, where p is the adjoint state, then you realize that here in general, I would have b of x, m, and alpha times p. And because b is just alpha, I have this inner product or dot product between alpha and p. I will use the two notations interchangeably. And here, because I'm in dimension 1, it will be just alpha times p. Alpha will be a real number, and same thing for p. All right, so this is my Hamiltonian. You can express it in the form h0 of xp minus f0 of xm. And h0 is the convex conjugate to L. Okay, so the convex conjugate here, I will use sometimes the notation star, so L star to denote the convex conjugate, and it is defined in this way. So this is for the continuous Hamiltonian. I'm going to focus on this setting also to explain the numerical method. But again, in the numerical method, we have approximated the gradient by a two-dimensional vector instead of just dimension 1. So I just say that P would be dimension 1. Here, P would be dimension 1. Alpha would be dimension 1, except that at the numerical level, we replace P by P1 and P2. So the derivative coming from the left and the derivative going to the right somehow. So for this reason, we introduce a discrete Hamiltonian, h tilde 0. So there is a tilde here, which takes as inputs x0, P1, and P2. The discrete Hamiltonian, we are going to assume that it satisfies some properties, and I give an example below. So in particular, it should be monotone, consistent with h0, differentiable, and also convex. Of course, for this we make the assumption that H is convex, and so in that case we can obtain that we can find an H tilde 0 which is convex. So because H tilde 0 should be consistent with H0, of course you need some assumptions on H0 in order to get convexity, for example. So let's take a simple situation where H0P is P squared. So what does it mean intuitively? If you think of P as a gradient of U and gradient of U as your control, then it means you pay a quadratic cost in your control. So a quadratic cost to move. It doesn't mean that the setting has to be completely linear quadratic, because if you remember, the linear quadratic case was linear and quadratic also in M bar. So you interact with the mean only through, you interact with the distribution only through the mean. Here, it's not going to be the case. We are not going to interact with the mean. So a possible choice in this situation is to take h tilde 0 equals the negative part of P1 squared and the positive part of P2 squared. The discrete solution, instead of taking U and M as functions of time and X for any point in the torus, we are going to represent them by vectors of dimension nt plus 1 times nh for each of them. Let's start with the discrete HJB equation. This is where there will be fewer surprises. We replace the time derivative by the dt operator we have defined before. So dt of ui is a vector. Here, this is a vector. And when I write n, it means that I take the nth coordinate. Okay, so dt ui, sorry, so let me, yes, so ui is the ith coordinate in space, but you have all possible time steps. You evaluate dt, the operator dt, and then you take the nth coordinate for the nth time step, if you want. Oh, time step. You have the second order derivative or its approximation, and here you see the discrete Hamiltonian where we plug the approximation to the gradient. I put in the right-hand side the terms that depend on M. So you see, this is where we take advantage of the fact that the Hamiltonian has a separable structure. Basically, the terms that depends on M is not completely coupled with the gradient of U. I mean, it is coupled, but in the right-hand side. So it's not a multiplicative terms that I have to keep in the left-hand side. And the terminal cost. Okay, so this is our AJB, discrete AJB equation, but you see that it involves the vector M. So I have to write the equation for M. How do we discretize the KFP equation? So we have this term in orange for the divergence. And this is the one that we are going to spend just a little bit of time to discretize properly. And if you want more details, this is explained in the paper of Ajdu and Capuzzo-Dolcetta, and follow-up also papers with Fabio Camilli and co-authors. So just let me know if you want more details, but here I explain the main idea. So you take this divergence, and I'm claiming that the discrete equation is going to be this one. I mean, that's the one we are going to take. The first two terms are not too surprising, but we have to explain this one. What is the operator Ti? So again, remember that Un will be a vector because it has all the possible points. So here I have NH dimensions, and same thing for Mn plus 1. By the way, you see that here we are using, this is an implicit scheme in the sense that here I plug Mn plus 1, Mn plus 1, and Mn plus 1 is also present in this dt. So this is going to be an implicit scheme, implicit in time. The discrete transport operator is given by this formula. So it looks a little bit complicated. You have some products which involve M and which involve H tilde 0. But let's just look at the intuition. The intuition is obtained by looking at the weak formulation. So you take the divergence that you had in this PDE. So let me take this term, plug it here, and I integrate it with respect to a test function W. Then you integrate by part. You get the gradient of W, and we try to mimic that at the discrete level. So at the discrete level, the integral becomes a sum. You have an extra minus sign because Ti here corresponds to minus divergence. This is a convention. You could of course put an extra minus in T, but that's why there is a minus here in front of H, and you have this discrete sum. Then you do some discrete integration by part here. So this is the equivalent of the continuous integration by part, and what you obtain is exactly this term. So in some sense, it matches exactly the definition we had of the gradient with two components in this way. All right, so we obtain this discrete system with two forward-backward finite difference equations. And this is what I mean by the numerical scheme. We have approximated the continuous system by the discrete system. I haven't proved it's a good approximation, but that's our candidate. And in fact, you can show nice properties for this system. It gives a monotone scheme for the KFP equation, which is one reason why we have discretized the transport operator in this way. You can show convergence to the classical solution when the scheme goes to, when the step goes to 0. So what I mean by that is you will let H go to 0, and you will let delta T goes to 0. So the step size in space and time, you let them go to 0. So each time you have for every choice of H and delta T, you have a different discrete system. If you solve this discrete system, you obtain a discrete solution. And this discrete solution converges to the continuous solution. So another nice property is that sometimes it can be used to show existence of solution to the PDE system. So what you do is you fix H and delta T. You obtain a finite difference system. You get the solution, UM. So this is um for this given h and delta t. So you get u, let's say, parameterized by h and delta t, and also m parameterized by h and delta t. If I change h and delta t, I get a different solution. And you show that this converges to some object um when h goes to 0 and delta t goes to 0. So if you already know that the MFG PDE system has a solution, then you just need to show that it converges to the right limit, to the correct limit. But maybe in some cases, you just show that it converges to something, and this something solves the PDE system. And so you have shown existence of a solution to the PDE system. So it can also be a way, looking at these discrete systems, can be a way to prove existence for MFG continuous systems. So we also respect the properties that the KFP operator is the adjoint to the linearized Bellman operator, existence and uniqueness for the discrete system. So here you can check these works of Ashdu et al. And it corresponds to the optimality condition of a discrete optimization problem. I will come back to this later when I discuss the variational point of view. What else can we say on this system? You see that we still have the coupling because so U has a terminal condition, M has an initial condition, M appears in the backward equation, and U appears in the forward equation. So we do not escape somehow the fully coupled system, which means that if I want to solve this system, I still need some non-trivial algorithm because I need to solve the forward-backward system. Compared with the ODE system, there is one more dimension because we have space. So you remember in the ODE system, we had only the n for time, but here we have n and I because there is also space. All right, so I don't know if everyone in the audience is very familiar with finite differences or not. Maybe what I'm saying is trivial, maybe it's very complicated. Feel free to ask questions in case something is not clear. So now let's turn our attention to algorithms. How can we solve this discrete system? And by solving, I mean compute U and compute M for every time step and for every point of the grid in space. So if I ask you to come up with an algorithm and you have followed the previous lectures, probably one suggestion you can make is to use fixed point iterations. And maybe you don't even need to have the previous lectures for that. You have this forward-backward system. A natural idea is to iterate between the forward and the backward equation. So here I add one extra superscript, K. So K denotes the iteration. So UK is an object in R nt plus 1 because I have nt plus 1 time steps, and nh, I have nt plus 1 points in time, nt time steps, and I have nh points in space. So UK is an object like this. You can represent it as a matrix or a very long vector. And it solves a discrete equation in which I plug. So if I want to compute, the next one at iteration k plus 1, what I do is I plug the m coming from the previous iteration at iteration k. So if I do that, then there is no coupling. I can solve the backward equation. If I want to do the same thing for m, then I have mk plus 1. I have just computed uk plus 1, so I can plug it here, and I solve the forward equation for m. You may notice that I'm writing immediately a version with damping or regularization or smoothing, or depending how you want to call it. But the idea here is you define m tilde k plus 1 as the average of the weighted average of m tilde k, which was your previous guess for m, and the new m that you have just computed here. And doing so, you are hoping that it will smooth the iterations. Maybe pure fixed point iterations would fail to converge. I've shown some example yesterday. But by introducing this damping, usually it helps a lot. and at least if the damping is strong enough, so you can hope to have convergence in this case, at least experimentally. So I hope these algorithms make sense. I don't see any questions, so I will just continue, and I'm going to illustrate it very soon. Before that, I would like to mention that the AGB equation is nonlinear. So here I said in a hand-wavy way that you can solve the backward equation, sure. But if you look at this backward equation, it involves this term h tilde 0. So this part here could be problematic because in general it would be nonlinear. So I gave the example later. If you want, you can have in mind the quadratic case. So dhu has two components and h tilde 0 is quadratic in each of them. So you don't really escape the nonlinearity. And you want to solve this nonlinear discrete equation. So one way to get away is to say, okay, I don't want to involve dhun here. So I will put the previous iterate. Because anyway, I'm using an iterative method, so why not plugging the previous iterate? If I do that, then there is nothing nonlinear, because you see here I've replaced the dhun by the previous one, so du appears only in the other terms, and there is no nonlinearity to solve. Another idea, because this one it introduces even more, relying even more on the previous iteration. So if you don't want to do that, another idea is to really solve this nonlinear discrete equation using a nonlinear solver. So the idea is you have a function and you want to find a zero of this function. So what is the function? Well, it's exactly what you had in the left-hand side. So this is the left-hand side of the equation minus what we had in the right-hand side. And you want these two terms to be equal. So you just take the difference. You take the difference for every n and for every I. So the function phi here is takes values in possibly large dimensional space. And also the input can be in quite high dimension. And you look for a zero, but we have good algorithms to look for zeros of functions. I discussed one yesterday, for example, Newton's method. So one possibility is to use Newton's method to compute the zero. So here there is a sample code. Maybe I can show it now. Let's see. Okay, I need to change the screen here. Okay, so I think you can see it now. So what do we have in this code? We are going to solve a discrete finite difference equation system, which is very similar to the one I described in the slides. There is a specific choice of running cost and terminal costs that are made. But you can find the details in the papers that are mentioned here. And what we are going to do is we are going to solve the Fokker-Planck equation. Write a solver for the Fokker-Planck equation, write a solver for the AJB equation, and then do the iterations between Fokker-Planck equation and AJB equation until it converges, hopefully. So I will skip the imports. You have some parameters. I will not describe the parameters, but I want to stress that here you need to define the Hamiltonian. If you want to do the mean field control version, which I didn't describe here, you need to compute maybe the derivative of the Hamiltonian. And most importantly, you need to define this function that you are going to try to solve. So here's what I call capital F is the same as the phi in the slides. And so I implement the function for which I want to find a zero. All right. Solver for the Fokker-Planck equation. So the Fokker-Planck equation is a linear equation. In fact, if you give me u, then the Fokker-Planck equation is linear. And here we focus on local interactions, meaning you interact only with m at your own location. So there is no integral to compute. And if you write the discrete equation explicitly, you look at the coefficients, you are going to see that you can rewrite the equation as just a linear system to solve at each time step. It is a system to solve because here we use an implicit scheme. If you use an explicit scheme, then to propagate the information, you just multiply by a matrix between each time step. But because we use an implicit scheme in time, then you have to solve an equation, but it's a linear equation. So the way it works here is that there is a loop in time. So you start with time 0, this you know m0. Then there is a loop in time from time 1 to nt plus 1. And at each time step, what do? You build a matrix. So I will skip the details. You build a matrix, and then you build the right-hand side, and you solve a linear system. So here again, I use sparse matrices. So I rely on this method. It's one possible choice. There are many ways to improve that, but one choice here is this one. So you solve a linear system, which gives you m at the time step k, and then you iterate. So this k is not the k of iteration of the meta algorithm. It's just for the time step. So this was the easy part in some sense. The more complicated part is the AJB equation. So the AJB equation, intuitively, here is going to be a loop backward in time. So we are going to start from the terminal time. We know the terminal cost, and then we go backward in time, starting from nt minus 1 until 0, time 0. And here it takes one line of code, but it relies on this function that I have implemented before. So you see that this function is going to depend on mk at time step n plus 1, and the goal is to get u at time n. M has been computed in the iteration just before, or in the same loop, but you alternate between Fokker-Planck and AJB. So you have M because you have already computed, or at least you have a guess for M. It's not the correct one yet, but you have a guess for M, and you can plug it here. So what do we see in this function? Get un with M. So you give me M, and I want to find un. There is a loop for Newton method. So here I really implement a Newton method naively by hand, just to show how it works. And you see that you have some number of iterations, and at each iteration, what you do is you get the new u by applying one step of Newton method. So this is a loop to the Newton method, and I have to explain this part, right? By the way, yes, you see that here, this is just to check if we have converged or not, if Newton method has converged or not. So let's look at the other method here. And in this one, you will realize that what we do is we get f and u, and then we compute basically the derivative of m. And this is what gives us one step of Newton method. And you remember yesterday I said, well, instead of inverting the derivative of the operator f, what we do is we compute the derivative, we solve a linear system, and we get this UTMP, or what I denoted x tilde I yesterday, which is given by this solving this linear system. All right, so here we have solved the AJB equation by using Newton method at each time step. You could do that differently. You could try to solve over the whole time horizon using one single Newton method. You could also, as Ivajdu does, solve the whole forward-backward system using Newton's method. But that's not what I'm doing here. I'm just focusing on the AJB equation and solving step by step backward in time. And once you have that, once you have the Fokker-Planck equation and the AJB equation, well, you can use fixed point iterations. So here there is this method, solve AJB by pcar, where you start with U initial and M initial, and then you do a number of iterations. So now we are talking about iterations of the meta algorithm, which is for pcar iterations. So you solve the forward, you solve the backward, and you repeat like this. Here you have a bunch of lines of codes, but it's mostly because I want to print some information and I want to save the information as well. Here you see that the way we get U new and the way we get M new is using this damping. So actually here I'm even putting damping on both of them. So I put U new, which is theta. So in the slides it is delta. So this would be delta and 1 minus delta, and here delta 1 minus delta. So I put damping on both of them. And this is very empirical, but it helps to converge. Okay, plotting function, I will skip this. This is just to show the results. And then you have the main test. So now the main test is pretty simple because you just call, let's see, this is for initialization. So here I initialize by taking M equal to M0 at every time step, and I take U equals to the terminal cost at every time step. So you need to choose some initialization, and if you don't choose it well, it's harder to converge. Of course, if you choose it well and close to the correct solution, it's much easier to make converge. So here I don't really start close to the true solution, but saying that M is going to remain constant equal to the initial condition is not a very good initial guess, but it could be reasonable. And same thing for the terminal cost. It's not reasonable because you have diffusion, so it will for sure it will not stay equal to the initial condition, but it's just to have an initial guess. All right, and here you see that I call this method solve AJB FP by pcar, which is going to do all the work. So I already ran the algorithm. We can run it. It's not very fast, but it's reasonable, at least if you don't have too many time steps. Again, this code is just for pedagogical purposes. So there are many ways to improve it if you need a code that goes really fast and etc. So, but you see that at each iteration, it is going to print the difference between the new U and the previous U, so the L2 norm or discrete L2 norm, and it is going to print the same thing for M. It also prints a relative error version, and it also prints the total mass at terminal time because I want to make sure that mass is preserved. So you see, it's not perfectly preserved. It should be exactly equal to 1, but it's not perfect. But well, given the discretization, it's reasonable, I think. And you see that the mass at terminal time is still more or less 1. So we do have conservation of mass. And here you see for one iteration, it takes 11 seconds. So I did 100. Well, actually, I did less than 100 iterations because there is a stopping criterion. And after just 19 iterations, you have already the difference between two iterations, which is of 10 to the minus 6. So here it stops. This is the running cost that I took in this case. So again, we are on the torus. So 0 is equal to 1, basically. And you see that the cost is smaller here. And here it has a local minimum. So people are probably going to be attracted to this position and also a little bit to this one. But we also have some term to prevent a concentration of mass. And anyways, there is noise which pushes people a bit randomly. Terminal cost is 0. The initial density is concentrated around the center of the domain. So the question is how people are going to evolve in time. This is the evolution of the value function. So you have x between time 0 and time 1, and here you have time. The grid is the grid. The numerical grid for the scheme is finer than what you see here. There are more points than just 5 or 6. This is just for the plot. And you see that the value function starts from 0 because this is its terminal condition, and then it decreases, and you can see these two shapes. So the value function is going to be minimal, close to the two minimizers of the running cost. And this is the evolution of the density. So it starts somewhere concentrated around the middle, and very quickly it takes two bumps on each side. So you see, it takes just a very, very short time for the density to spread and to concentrate around the two minima or local minima of the running cost. And you see also that the solution doesn't change too much here. Towards the end, it changes a little bit, but for a relatively long time, it's more or less constant. So I will come back to this, but this is called the turnpike phenomenon in mean-field games, and not only in mean-field games. And the idea is that if you take a long enough time horizon, then the solution has some behavior close to time zero, some behavior close to terminal time, and in between, the solution is more or less constant, constant in time, at least for the density. So we have seen that for the value function, it's not the case because the value function scales with time. If you have more time remaining, the value is different than if you have less time, but the density is basically stationary. So that can also give you an idea if you have a mean-field game to solve on a long time horizon, maybe you don't need to really discretize the whole time horizon. Maybe you just need to understand the beginning, the end, and the stationary solution. Convergence for U. So this is the difference between U new and U old, the L2 norm or discrete L2 norm. Remember that the U new has some damping. So if you put a very, very strong damping, you cannot hope for a lot of difference between U new and U old. So if you see a very tiny difference, it might be just because you have chosen a very strong damping. And then, of course, it cannot involve much. Here, I think the damping was, let's see if I can see it somewhere. I think it was above, I took 0.5. So you see that the difference between two iterations, at some point it decreases, then there is a kind of plateau, and then it decreases and it finds its way towards a good solution. And the convergence for M is in some sense more straightforward. This is the final density that you get, and as expected, it's concentrated here and here, even though the terminal cost is zero. So the density is concentrated here and here because of the running cost, not because of the terminal cost. And the total mass and U at terminal time, etc. So you can try other things if you like. We can try. So let's see if we put a damping of 0, meaning. So what does it mean? It means that I give a 0 weight to. Okay, sorry. So here theta is 1 minus delta. So I should give theta of 1, meaning that I give full weight to the new U, and I give a 0 weight to the previous U. So if we try to do that, let me try to run all. So I hope this is not boring for you. I try to make things more concrete, but of course you can play with the code later on. So, okay, so here everything has already run. So let's see. Now you see step by step, it is going to print the information. And let's see. So at the beginning, here you have U like this. The difference between two iterates is like this. And here it decreases a little bit. So it's good. But now you see that U, the difference between two iterates of U increases. And the difference between two iterates of U increases compared with the previous one. So that's not very good. Now it's still increasing, so it's still not very good. So it doesn't look like it's going to converge. Okay, you can run it for more time. For the sake of time, I will just stop here. But you can run it for many more iterations, and maybe if you wait more, it converges. I would bet that it does not converge because I did the test before, and that's why I put a damping coefficient of 0.5. Of course, it depends on the time horizon. It depends on the other choices of coefficients. So depending on your model, there is no one perfect answer for the choice of the damping coefficient. But you have to try and see depending on your model. Any questions about this code or this method? So apparently no question. So
there will be a question in one minute, maybe.
No.
Okay. Okay, sure.
I know there is one remark on the chat.
Ah, yes. Okay. Let me take the remark. Oh, I share the slide. Okay, well, thank you for the remark. So, all right, so you can play with this code. Again, this damping idea is a relatively simple way to fix the pure fixed point, but there are other methods. So don't take it as a panacea that can solve every mean-free game that always works. But I think it's a relatively simple to implement method, and it can work if you use a suitable damping coefficient. So the other method that I mentioned that was introduced by Ivashdu is to use Newton's method for the whole system. Because if we go back, so now I go back to the forward-backward system. Here, you have this system, and you remember what we did in the ODE case. So in the ODE case, we had Z and we had R, and I said you take a vector, you define a function f such that this should be 0. So this function f encompasses the whole forward-backward system. And then you look for a 0 of this function using Newton's method, for example. So here you can do the same thing with U and M, actually. So you have more dimensions. I mean, there is one more dimension for space, but you can concatenate all the coordinates in time and space, and you can write a very long vector of U and M together. So I formalize this a little bit here. You take U and M, and in fact, you have two components in your function. You want to solve the discrete HJP equation, the discrete KFP equation, and together it gives you this function phi. Then applying Newton's method would mean computing the Jacobian of phi at the point xk, where x is now has two components, but in fact it is in dimension number of time steps multiplied by number of space in time multiplied by 2. And then inverting this Jacobian. But inverting the Jacobian is typically expensive. So one thing you can do is to just rewrite this as an intermediate step to solve a linear system. And then you add this in order to get xk plus 1. So in the end, the key step is this one, where the unknown is y, and this amounts to solve a linear system for which you can compute actually all the coefficients. So I'm going to skip this for the sake of time, but you have more details in the papers of Ivashdu and Capuzzo Locetta, Fabio Camilli, etc. So then there is nothing non-linear to solve. Somehow each step boils down to a linear system to solve. So as I briefly mentioned before, whether we are talking about this Newton method or whether we are talking about the fixed point or other methods, of course, it's better if you start from a good initial guess, because if you start from a bad initial guess, it's harder for the method to converge. And if you have only local convergence, when you start far away, maybe it just does not converge. Maybe you can prove it will not converge. So you really need to start with a good initial guess. So one way, what I've shown in the code was just to start with the initial M0 and the terminal UT everywhere. It's not such a good idea. Something better would be to start with the ergodic solution. So you can solve the ergodic mean-free game. I will come back to this setting when I discuss deep learning in lecture 5. I will show one example. But you can solve the ergodic problem using finite differences, and then plug this solution as an initial guess. Why is it a good idea? Well, because of this turnpike phenomenon that I've shown. So the solution is more or less stationary, at least for a long period of time. So if you take that as an initialization, maybe it's a good initial guess. Another idea is to use a continuation method to start with a high viscosity and then solve the problem, use that as an initial guess for the problem with a smaller velocity, smaller viscosity. And this works because it tends to work well because when you have a large velocity, the problem is very smooth and the solution is easier to compute for the algorithm. So you solve this one and then you decrease the viscosity and continue.
So Mathieu,
yes,
I just put a question in the chat.
yes.
So when you say that you initialize from the ergodic solution, you mean that
yes.
the ergodic solver is easier to implement than the non-stationary one?
Yeah, I think in some, I mean, at least in some settings, it's easier to solve the ergodic problem and to compute the stationary solution, and then to use that as an initial guess.
So are you going to speak about the analog of what you did today, but in the ergodics, in the stationary setting, and say how to solve the Fokker-Planck equation and especially the Hamilton-Jacobi equation?
No, I was not planning to talk about that, but
Okay.
it's a good point. Maybe I can add something later, or we can
No, this
discuss
was
it.
just a question. No,
Yeah,
I was
yeah,
wondering
thank you.
because there are some subtleties for the Hamilton-Jacobi equation in the stationary case. Okay.
Yes, I agree. I think the ergodic case, yes, for meaningful games is not always so easy. So, okay, my point is more if you manage to solve it, if you have a method to solve the ergodic problem, then you can use that as an initial guess. Let's put it this way, maybe.
Okay.
Yeah, thank you. It's a very good point. Would you advise any preconditioning? Yes, so indeed, preconditioning can be a good idea. I think I mentioned that just a little bit later, but without going into the details. But yes, preconditioning is a good idea. Let's see. I think I mentioned it a bit later, so let's see. One example that we solved with Ivajdu using this approach. In fact, the same approach works for meaningful control, for the meaningful control PD system. So I'm going to show both. And this is based on an example where you have a room. You are going to have people located between the obstacles. So you can think of I don't know, a movie theater room or something like this. And people are here and they want to exit here and here. While avoiding the congestion if possible. So this is the initial condition on the left. You see the density split into several pieces and the final cost on the right. So the final cost is smaller. In fact, it is 0 towards the exit. But if you are at the back of the room, the cost is expensive. So your goal is to not be at the back of the room at terminal time. And we fix a time horizon in this model. So here it will be a crowd motion example with local interactions. All right, I think, let's see. I think I clicked on a link and okay, what if I do this and then I do this? Okay, this was part 1, sorry, part 2. Oh, okay, so apparently there is something that he doesn't like. I'm sorry for that. Okay, let me try to fix it. So I will stop sharing and I will do it again. Okay, so, all right, I think the problem is fixed. Let me share again. I need to do this. Okay, I think there was a link somewhere. I clicked on something. So local interactions. There are other models with non-local interactions. So you can take a look at these references. Here, again, the player controls her velocity directly, and the Hamiltonian is of this form. So I leave it as an exercise. What is the cost function leading to this Hamiltonian? You know the drift, because the drift is going to be just alpha. You know the definition of the Hamiltonian. So question, do some reverse engineering to find the running cost that led to this case. And in fact, you are going to see that the running cost is something related to the congestion example I gave before, which was basically some multiplication of t and x. So let me write the stochastic version. Maybe you take m at time t and position xt, and you multiply by alpha of t and xt to some power. So here you can put some power gamma, and here you can put some power delta, for example, 1 and 2 respectively. And this means that the cost to move increases when alpha increases, but it also depends on the number of people at your location. So if there are many people at your location, you pay a higher price to move than if there is nobody. And the normalization, the constants are a bit special because we want to have some interpretation for this model. Okay, so I think the problem is back. Yes, I think I know what is going wrong. It's probably because I have a video later on and and probably the iPad does not like this too much. All right, so the PDE system looks like this. So you may recognize the Hamiltonian here, and also the derivative of the Hamiltonian in the equation below. The mean field control problem has one more term. So you notice that here you have this extra term, which is related to the fact that you have somewhere the derivative of h with respect to m. We take a small viscosity coefficient. So because in practice, there is not too much Brownian motions when people move. Usually it's not very stochastic, except maybe when you are pushed around or something like this. But otherwise, it's not very stochastic. So you want a small viscosity. And here we start by solving the problem with a high viscosity and then use a continuation method. The terminal cost actually is, yes, you can take the terminal cost 0 and the running cost as I described before, or you can put also a terminal cost like the one I described in the previous slide. And we put Dirichlet condition at the doors and a Neumann boundary condition on the walls, so the walls of the room and also the walls of the obstacles. And this you can implement relatively easily in the finite difference scheme because you have the discrete equation, so you can decide to change one point. You can decide to change the value at one point by imposing an extra constraint. The initial density, I described it. Time equal to 0, we interpret this as, so we interpret, the density is 1 because we normalize everything, but we interpret it with this number of people, and we interpret the time as 50 minutes. To do this, you need to play a little bit with the constants in your model and to come up with an interpretation, but we don't use a finite number of agents. We really use a mean field game, and we say that when the density is at this level, it means this number of people per square meters. So for example, 4 people per square meters. It's just an interpretation. Okay, so this is a video that probably the iPad doesn't like very much, so I will not click on it, but you can download the slides and click on this animation to see the evolution of the mean field game on the left and the mean field control on the right. I will show some step-by-step evolution. So this is at time 0. They are similar. You see, you have indeed 4 people per square meters here. And then they're going to diffuse and not only diffuse, but evolve towards the boundaries and move towards the 2 doors. So again, mean field control means a cooperative scenario, and mean field game means a Nash equilibrium, so the more selfish scenario. So here people move. You see that there are fewer people at the center and more people towards the side, and you see that here for mean field game, it decreases pretty quickly at the center. For mean field control, not so quickly, right? So it looks like mean field control is not doing very well because after all, people want to exit the room. So if they keep waiting, they are not going to exit the room. But then you keep moving on like this, and you see that at the end, both of them, so this is 4 different time steps, and both of them manage to reach density 0 inside the domain. So here, if I go back, you notice that there is one point where here there is a high density for mean field game, whereas for mean field control, it is lower. The interpretation that we can make is that people in a mean field game are somehow trying to exit as fast as possible because they are selfish. They are anticipating other people's move, right? It's not a pure dynamical system. Again, we are really solving the mean field game, so we are really trying to anticipate the behavior of the crowd and trying to act in our own best interest. And our own best interest is to try to move relatively quickly. Whereas in the mean field control, apparently, people wait more because you remember this, people are waiting a bit more. But the consequence is that there is less congestion because the density remains at a lower level globally. So we may wonder what happens to the exit time and what happens to the density. So here, all right. So in this paper, we added a few plots. In particular, you could look at the remaining mass in the room. So here, this is time, and you see that the remaining mass inside the room at every time t is globally larger in a mean field game than in the mean field control, right? The red curve is above, meaning that, in fact, people exit faster in a mean field control problem when they are behaving in a social way, which is intuitive, but in real life, we are maybe worried that if we behave in a cooperative way, it's going to be bad. But actually, on average, it's better. And you can also look at the price of anarchy. The price of anarchy is at least 1. And when you play with the coefficient beta, which is the exponent in the Hamiltonian, there is 1 plus m to the power something. So this something is beta. And when you increase beta, the price of anarchy increases. At least that's what we see numerically. Intuitively, I think this makes sense because if you have this coefficient, 1 plus m to the power beta, and you increase beta, it means that you increase the influence of mean field interactions, right? So mean field interactions are through the cost, are through this term here. So if I take beta larger and larger, I'm increasing the impact of the crowd on myself. So intuitively, it should increase the price of anarchy because you're going to see a bigger difference. When beta is equal to 0, this term disappears. So you are back to a pure alpha squared term in the cost, purely quadratic. You pay a quadratic cost to move, and it does not depend at all on the crowd. So there is no price of anarchy. You are going to behave exactly in the same way, no matter how many people are around you. Here you can see 3 curves. Maybe I can zoom in a little bit. You can see 3 curves obtained for different values of nu. And you see that when nu decreases, so the last one is the smallest one, when nu decreases, the price of anarchy increases. Again, from a point of view, it makes sense because if you have a lot of diffusion, let's take an extreme case where you have a huge diffusion, then somehow whatever you do, it doesn't really matter. You are going to get the same solution. So you cannot see much difference between mean field gain and mean field control. But with a smaller diffusion, then you really see people can really control their velocity almost exactly. And then you see more difference between the game and the control setting. All right. I don't know if there are any questions, further questions. Otherwise, I will move on to the semi-Lagrangian scheme. Okay, so semi-Lagrangian scheme is still a scheme for the PDE system, but the idea is a bit different. Instead of using the AJB equation, we are going to use the interpretation of the value function using the sum of future costs. And we are going to build a numerical method on that. So this scheme was introduced by Carlini and Silva. There are these 2 papers and there are several follow-up papers. So for simplicity, I take dimension 1. The state space, let's say, is R, and the action space is R as well. So in practice, you may want to use a bounded domain, but here for the explanations, it will be the whole domain. We take nu is equal to 0. So this is one nice thing with the scheme. It works with nu is equal to 0, which is a bit challenging in the previous method that I presented earlier. Again, the drift is the control, and the running cost is quadratic in alpha, but this is not a linear quadratic model because the dependence on m could be different from the mean. And in fact, here this m, as in the previous case, maybe I could have stressed that even further, this m plays the role of mt xt. So this is what I mean by local dependence. So this m is basically a real number, right? So f0 is a function from r times r to r. It's not a function that takes a probability measure as an input. So we have local dependence, and in particular, it cannot be a dependence through the mean because this is a non-local dependence. Okay, sorry. Actually, in this model, sorry, so it's written below. Actually, in this model, we can take a non-local dependence. So here, let me correct that. This was for the previous model of congestion, sorry. So here we have potentially MT, and here we have P of P of R to R. So what I said was more for the previous model of congestion. Okay, so let's see what happens here. So in this case, the MFG-PD system takes the following form, where you have the backward equation and the forward equation. Let's try to rewrite the representation, try to rewrite the value function using the definition. So the dynamics of x, because there is no diffusion, is given by the integral of alpha, in fact, between time 0 and time little t. The value function is the integral. So if you use dynamic programming, the value function is the integral between time t and time capital T of the running cost. So this is the function f plus the terminal cost. I want the optimal value, so I minimize over all controls, and here we take controls alpha, which are in L2. Yes, maybe one comment. So I don't need to take feedback controls. Why? So you notice that here alpha is a function of time only. Why we don't need to put x? Because the evolution is deterministic. So if I know x0, and if I know what time it is, and if I know which control I am using, then I know exactly x at time t. I can predict it perfectly. So then we can write discrete equation corresponding to the continuous equation, where we have a flow of densities given to us, and we write a sort of dynamic programming equation backward in time. And this is based on the operator S. So here we have to explain what is this operator, and what it does. It mimics what we had in the continuous case here. So except that we do that for one step. So this is one time step. You see, time step Tn. And after that, we write this I here. So what is I? It's going to be a function of W, which is also in the left-hand side. And W, you can think of it as U at time n+1. So we are trying to compute U at time n. We already know U at time n+1. And based on that, I'm going to compute this quantity, I of UN+1, and I'm going to add the cost for one time step, and this will give me the value at time UN. So I is basically an interpolation operator based on basis functions. So the beta i's here are triangle functions on xi-1 and xi+1. And the idea is really just to take the sum of u at the next time step to interpolate. And why do we want to do that? Why do we need to interpolate? Because at time tn, so imagine that at time tn, I have a plot just after that, but at time tn, we are at position xi, and we use control alpha. If I do that, I end up at xi plus alpha delta t at time tn+1. But the problem is this point maybe is not on my grid. I have discretized space, but maybe this point is not on my grid. So in order to compute the value at this point, which is not a point in the grid, I interpolate. So, all right, once you have this, you can define the function little u. So little u is really going to be a function of t and x obtained by interpolating the capital U. And in fact, this function might be non-smooth. So what Carlini and Silva propose to do is to regularize it by taking the convolution with for example, a Gaussian kernel. So again, the idea is we start from the function capital U at time n+1. From here, I obtain U at time n, and then I get the function little u. Let's say, in fact, any point in time if I want, because I can take t divided by delta t. So here we just use somehow the closest time point. And u here, so this is a vector for different I. This is a vector for different I. Sorry, and this one is a function of t and x. So we have 2 points of view. In fact, the Eulerian point of view, where we focus on a location, and then we look at the flow going through this location, and so then we look at the velocity at t and x, and this characterizes the evolution. And the Lagrangian point of view is more looking at one parcel of the fluid, or the population in our case, and looking at how this parcel is going to flow during future times. So here in our model, the evolution is deterministic. It is given just by alpha integrated over time. So here is a diagram to represent what happens. Imagine that you are at time t or tn. So this is tn and this is tn plus 1. You have the discretization in space on the horizontal axis, and imagine you are at xi. Let's for now forget the m, the density. The m represents somehow the histogram of the distribution. Let's forget about it. Let's just look at xi. You are at position xi, and you take an action alpha I n for time tn. You end up here. So this point, unfortunately for us, is not on the grid. It's not on the grid, so what can we do? Okay, so one idea could be to project, but something better is to use interpolation. So we use these basis functions, beta j for every j on the grid. And then we are going to look at these two values. We are going to look at the value of u n plus 1 at point j. So how much value we have at this state, how much value we have at this state, and we are going to combine this with these two coefficients here and here. And we are going to do a kind of weighted sum. So that's the basic principle. You do this weighted sum, and then this tells you how the mass should evolve. Intuitively, if you want, in some sense, it amounts to say that people who are, so let's now look at, so okay, let's use the single agent point of view. You are here, let me go back. So you are here and you jump to the location in purple, but in practice, we don't want someone to end up here. So we say, okay, you are going to go to xj, or you are going to go to xj plus 1. You have to choose. But in fact, you don't want to choose in a deterministic way, so you choose in a probabilistic way. So you are going to choose xj with some probability, and you are going to choose xj plus 1 with another probability. And how do you choose the probability? Well, you choose proportional to more or less to the distance, in fact, proportional to these beta j's. And so for a single agent, it means we would need to do some kind of Monte Carlo simulations, but we don't look at a single agent, we look at the distribution. So if you look at the distribution of agent, concretely, it means that the mass present here is going to be split into one part for this location and one part for this location. So that's what happens at the microscopic level. And this is particularly well suited for mini-field games because we look at the density of agents. So this M is split using the formula. So that I'm going to write next. This was a diagram to give the intuition. So what is the formula? The control is given by minus the gradient of u. So you see, that's why we really wanted to have a function so that, and a regular function, so that we can compute the gradient, because it is the gradient that gives us the control. Then you write the equation for the discrete flow. So basically you take xi and you add alpha hat multiplied by delta t. Okay, and in order to get the KFP equation, you use this phi epsilon defined above, and then you evaluate beta, which is the hat function, and you multiply by the mass at the previous time step. So here we want to have time step n+1. You use the mass at time n, and you move it forward, but you split it depending on where phi takes you. If it's a point in between beta j, xj and xj+1, then you split it into 2 parts. So I hope this makes sense. You see that the point of view is really different. So the point of view is really to use this Lagrangian approach in order to let the mass evolve, and the value function is defined not using a backward differential equation or finite difference equation, but really using the definition of the value function as the sum of future costs. All right, so one thing we need after that is to define a smooth version of m as a function of t and x. So you do that by interpolating actually it's not necessarily that smooth, but the epsilon here, sorry, is there because m epsilon itself depends on the gradient of u epsilon. All right, so once you have that, in fact, the problem boils down to a fixed point equation again. So let me stress this. You start with m hat. So you start with m, maybe you have some initial guess. Let me write k for iteration k, which is a vector or a matrix if you want, or a vector if you concatenate everything. Sorry, so I'm going to write it in this way, mkn. Then what you do is you compute m epsilon delta t h of this. So this is going to give us this component. And after that, you take, you get mk+1 from here. Now, this part is the complicated part, because if you look at it, it is defined above. So we go back to the definition above, but it involves this m epsilon, which itself depends on alpha hat, and alpha hat depends on gradient u epsilon, which depends on the capital U we have computed at the very beginning. So it is a fixed point equation, and it involves the value function. The value function didn't disappear completely from this landscape. So, okay, let's see. I have the code a little bit later. Let me just say that there are different ways now to solve this fixed point equation. It is a finite dimensional fixed point equation because m hat is a vector, and you can use some of the techniques I've explained before. So Carlini and Silva used fixed point iterations, pure fixed points or damped fixed point iterations. I have a code to illustrate that, but you could imagine maybe other techniques to update the iterations. I mean, to do the updates between each iteration and to converge towards a fixed point. Here is a numerical illustration. So terminal cost is equal to 0. F is equal to this term. So here, again, this is non-local interaction, where the non-local interactions are smooth in the sense that you take m, which is the probability measure, and you take a convolution. So if I want to compute this convolution, I really need to have m defined everywhere. So so that's why it's convenient to work with really m as a function of t and x as an input to f. So again, let me stress that just to avoid the confusion I had at the beginning. So this m is an element of p of rd, or p of r here, because we're going to be in dimension 1. Okay, and for the convolution to make sense, probably you want some condition. So 1 over alpha square is the cost to move. Then you have this, which is some kind of spatial preferences. So preference in terms of location. So C star is going to be a preferred location where people want to go. Then you have a normalization, just a constant to give more or less weight to this term. And you have 2 regularizations here for V, which is a function of M. So this is a model that take Carlini and Silva take in their paper, unless I modified it a little bit, maybe, but I think it's pretty much, it's quite close to the models they consider. And the experiments I'm showing here are for the target C star equal to 0. The initial distribution is split into 2 parts. So you can see that at time 0, you have 2 parts for the distribution. And on the left, you take kappa MF equal to 0.5. On the right, kappa MF equals to 0.9. What does it mean? It means that we are playing with the influence of the mean field term. If kappa MF is 0, then the mean field interactions completely disappear. If kappa MF is very large, it means you feel very strongly the interaction of other people. And the interactions, you see here, this term is going to increase if M is large near X or around X.
Mathieu, there is one question in the chat.
Yes, thank you. Sorry, is C star given or unknown? So yes, thank you for the question. So C star is known and it's part of the model. So we choose it at the beginning and it is known by the agents when they solve the problem. So here, C star, I choose it to be equal to 0. You could put another location. It means the agent will be attracted to this location. Attracted in the sense the cost will be smaller if they reach this location. Thanks. What else? Okay, so this is the initial distribution with 2 parts here and here, and people are attracted to 0. So what we see on the left is that if kappa MF is small, meaning people don't feel a lot the congestion cost or the crowd aversion cost, then they will really concentrate towards 0. And you see that at terminal time, so the different colors are for different time steps. So the mass moves towards the center. It moves from here to here to here to here, and then it concentrates more and more at the center. However, if the cost of crowd aversion, so I call this crowd aversion, if you put it very, very strong, maybe it's agoraphobia, or maybe you really, really want to avoid the crowd. But here, 0.9 is not extremely large, but still. So you see that people move towards the center, but they stop before reaching 0, because the cost of getting closer would mean increasing the crowd aversion cost. Right? And if you take kappa MF even larger, maybe people will not even go towards the center. They will just try to spread over the domain because they really want to avoid mass. So maybe even this initial condition would be too much for them, and they would just try to spread the mass in order to pay a lower cost of crowd aversion. So let's see, maybe it's a good time to make a short break, and then I can show this code and move on to optimization methods.
Thank you, Mathieu. Are there any questions on the chat? Thank you. So if there is no questions, then we can resume in a bit less than 10 minutes. So 11:40. Is it okay? 11:40 for you, Mathieu?
Sure, sounds good.
Let's do this.
Thank you.
Okay, so there is one question. Maybe what we are going to do is to answer the question before we restart, because maybe Mathieu just left. Thank you for the question, Amal. So once again, Matthew is going to answer just before we resume. Thank you. Welcome back. So before we resume, Mathieu, there was one very nice question on the chat for you. I don't know whether you saw this question or not during the break.
Yes, thank you. So indeed, yes, thanks for the question. So the question is about what is a Jacobian matrix is singular in Newton's method. And so apparently you got this problem for small viscosity. So I think it depends on the situation. So indeed, for small viscosity, the problem could become degenerate in some sense. So it's not completely surprising, but I would assume that if you use the Jacobian also depends on where you evaluate it. So I would say that if you start from, again, a good initial guess, maybe you can avoid this problem of having a singular matrix for the Jacobian. If you avoid inverting the matrix, I'm not sure if you were trying to use the pure Newton method where you invert the matrix, or rather trying to use this small trick where you solve an extra linear system. Yeah, so I think it depends on the situation. Maybe we can discuss more later. And I would say, yes, definitely using this continuation method for decreasing the viscosity can help, but you cannot decrease it too quickly, otherwise the initial guess is not good enough. It's just an intuition. So yeah, if you have a specific example in mind, I'm happy to take a look later. If you want, we can take a look together at this specific example.
Thank you, Mathieu. Is there any other question before we restart? So there is no question on the chat, so Mathieu, please.
Okay, thank you very much. So I will just show a sample code to illustrate what I just described. Let's see. So here. All right. So this one is really based on the approach of Carlini and Silva. It's exactly for the case I described in the slide. So I will go quickly on the setting. Here there are not too many things to discuss. You can see here I define the functions for interpolation, so the beta functions and the operation of interpolation. Then there is a piece of code. So let me show the tracer. This is a piece of code to solve the AJB, a piece of code to solve the Kolmogorov-Fokker-Planck, and then the global solver doing the iterations between forward and backward. So here, this is the function to solve the AJB, which is basically like solving the backward equation in time, except you have to deal with the discretization in space. So you can check this operator S, but basically the idea is to really use the operator S to define U at time n and going backward in time. The Kolmogorov-Fokker-Planck equation, which was the part, maybe the less intuitive part, where we had to explain this Lagrangian point of view and how the mass evolves and split between two different cells. Here is summarized using basically just a few lines of code and defining this M epsilon, which is M epsilon, capital M epsilon in the slides. And you can see that it really relies on multiplying beta evaluated at phi by M epsilon at the previous time step. So M epsilon at the previous time step, we already know it. We can evaluate this function phi n, which basically moves the mass to the next time step. And then we need to say how to split it. And this is done by summing the betas, multiplying M epsilon. Global solver is just fixed point iterations in this one. So here I will skip it because we described it multiple times. And here you can see the evolution. So let's see. So at each iteration here, or let's see, or every 5 iterations, maybe I print. So at every iteration, I print some information, and every 5 iterations, I print the evolution of the mass. So you can see that after a few iterations, the mass is already moving towards the center. The value function, sorry, has taken this shape. So this is U epsilon for different time steps. So at terminal time or close to terminal time, at terminal time it is 0 because of terminal condition, but close to terminal time, it takes this convex shape. here, concave shape, convex shape here, we are minimizing. But close to the boundary, you see there is some straight line, and this is because at the boundary you have some boundary condition, which is somewhat artificial. This is for the numerical method, because in the what I described in the slide, it's supposed to be completely over the whole domain, right? But in practice, you may want, or you are going to solve on a bounded domain, and so the behavior at the boundary of your domain will maybe not be the exact one as if you were solving on the whole domain, on the whole real line. So we have this strange behavior, but in some sense, it does not affect the mass, because at time 0, the mass is between roughly minus 1.25 and minus 0.25. So you see the mass is here, and it's not affected by this perturbation at the boundary, and then the mass is going to move towards the center. So again, here there is some approximation, but in principle, it's not going to really affect what we see in terms of density movement. And then, so you have more and more iterations. I will go, I don't remember, I ran it recently. So at the end, what you see is the evolution of the mass for parameters that are slightly different from what I presented in the slides. The value function in the part of the domain that really matters, and the difference between 2 iterates of M and the difference between 2 iterates of U versus iterations. And you see that this goes towards 0. So we can claim that the algorithm is converging, at least numerically. Okay, so you can download this code again. I will go back to the slides. Sorry. I don't know if there are any questions about that, but I encourage you to try to download it and play with it and see by yourself. Okay, so another exercise, but it's related to something we already discussed. Try to implement the previous finite difference scheme, but for this MFG model that I described with the semi-Lagrangian scheme. So there are 2 issues. One is that we took nu is equal to 0, so probably it's not going to work immediately in the finite difference method. And the other issue is you have some non-local interactions due to the convolution. And so when you look at it from the finite difference scheme point of view, it means that you are going to have some discrete integrals to compute, and some matrices are going to be not sparse anymore. So you remember I made this comment about sparse matrices before. Here the matrices are not going to be sparse if the interactions are non-local. All right, so section 3 is about a different point of view where we interpret the PDE system using a variational point of view. So this is not always possible. It's possible for mean-field games that have a variational structure, and it's possible in general for mean-field control, because mean-field control PDE system always has this variational interpretation. But the method I'm going to present is not working for all mean-field control problems. You need some assumptions. But intuitively, the variational interpretation is by definition for mean-field control. So, okay, there are quite a few technical details. For the sake of time, I will not go into absolutely all the details. But the idea is you have the PDE system. You interpret it as the optimality condition for an optimization problem, and then you use duality to have a primal and a dual problem. And based on these primal dual problems, you can borrow. So based on this, you can introduce techniques from optimization. In fact, borrowing techniques from the literature on optimization. And I will present 2 algorithms that are based on this point of view. All right, so I already showed these slides before. It is just to say is that the variational point of view on infinite games is not new. In fact, it was already in the paper of Lazary and Lyons, the original paper, and then it has been used a lot, including by Pierre Cardaliaguet and co-authors, and Benamou and co-authors, among other people. So to explain the idea, I will take again this setting where the running cost is split into two terms, L and F0, and we have a separate dependence in alpha and L. Terminal cost is just a function of X. Then you have the Hamiltonian, you have the conjugate, the convex conjugate of the Hamiltonian. And for simplicity, we are going to take L to be equal to just alpha squared. So in that case, H0 is just P squared up to a factor 1/2. We will work on the torus and in dimension 1 to alleviate the notations. So what is the idea behind the variational problem? Remember that a mean-field game is really a fixed point problem, right? So what we do is, given alpha m, I try to optimize over alpha hat, and then separately, I impose that m hat should be equal to m generated by alpha hat. So two steps. I want to do the inf over alpha hat. Step 1. Step 2, I want to solve the equation that m hat should be equal to m alpha hat. So this is really a fixed point problem. Now we are going to interpret this problem using a variational point of view. So imagine we are already at equilibrium. You have alpha hat, you have m hat, and you write the cost for one representative player. So you can write everything as an integral with respect to m hat, whether it is for the running cost or for the terminal cost. So I get rid of the expectation, and this is subject to the evolution of m hat controlled by alpha hat. And because the drift is directly equal to the control, I can just plug alpha hat here. I can just write alpha hat instead of b. Okay, now I'm not doing any optimization. I'm just saying, if you give me alpha hat, you give me m hat, I can compute the cost, and it has this expression at equilibrium, if I am already at equilibrium. Next, we do a change of variable. We introduce w hat, which is m hat times alpha hat. So we take, in fact, exactly what appears in the divergence here, which is a product, and we define this as w hat. And this trick was used previously. Benamou and Brenier used it in optimal transport to have this variational viewpoint as well. And what is the advantage is that that in this case, you obtain an optimization problem where the constraint is linear. So the above cost here is rewritten as B, and the constraint is linear. Why? Because we don't have any product anymore. We have just the divergence of w hat. So if I use as my two variables m hat and w hat, the constraint is linear, and the cost under some assumptions is going to be convex. So you have a convex cost as a function of m hat and w hat, two variables with a linear constraint. And this is very nice because for convex problems with linear constraints, we have a lot of methods, a lot of algorithms, and also a lot of techniques from the theoretical point of view. Okay, so here I claim that we can interpret this problem as a convex problem with a linear constraint. So just to clarify things, I am going to introduce this L tilde and G tilde and F tilde here and here and here, so that we can write everything in this way. And now, okay, I claim convexity, so maybe it's not clear. We need to make some assumptions on L and F0. So L, I already say that I'm going to take it quadratic. And I need to say something about F0 and also about, so for G, I think it's clear because the terminal cost is just the integral of little g. which does not depend on M for simplicity, but F0 is a function of M. So, okay, for now, let's accept the fact that it's a convex problem with a linear constraint. So the goal is to minimize over MW this function B of MW. And what we are going to do is we are going to use duality and have a dual problem. So here I take, let's see. So actually, I provide some explanations here about F0. You can make some assumptions so that your function F tilde is indeed a convex function of M. And then for L tilde and G tilde, we are good. Notice that, let's see. Yes, notice that, for example, we need to be a little bit careful about what happens if, so we don't want to allow M to be negative. Here, there is one thing that I'm sweeping under the rug, which is over which spaces, over which space we are optimizing, right? We want to minimize B as a function of MW, but over which spaces we are optimizing. And in particular, we don't want to allow M to be negative. So if M becomes negative, we put an infinite cost, and this is going to be a convex function. So the dual problem is this one. Here, I just write it immediately. You can see that it's a function of phi, and you can think of phi as playing the role of u, more or less. So phi plays the role of u, and here we interpret it as some kind of adjoint variable. What do we see inside this new cost? We see, in fact, the AJB equation. So this is what we had in the AJB equation. And here we have something that involves time 0, whereas here we had something that involved time capital T in the primal problem. So how does the proof work? I claim this is a dual problem, so you can indeed show that the two problems are in duality in the sense that they achieve the same value. I call them A and B, and the proof is based on Fenchel-Rockefeller duality theorem. Again, here I'm sweeping under the rug the fact that I need to choose some suitable spaces. So I would need to say what is phi and what is MW, but you can make all of that rigorous. So here I refer to the paper of Kadaliage, or the notations I'm using here are from my paper with Ivajdu, but this was again already studied by Pierre Kadaliage and co-authors for first order and then second order degenerate Minfield games. Okay, so just some notations that I'm going to need later when I discuss a discrete setting, because we are going to do the same thing at the discrete level now. So here there is this function calligraphic f, this function calligraphic g, where f is basically the terminal condition must be satisfied. If it is not satisfied, you pay an infinite cost. And then you have the product of M0 and phi. And G is basically what appears in the AJB equation, which we have here. So it is written as a function of phi1 and phi2, but phi1 and phi2 are replaced respectively by these two components of the function lambda, which are the time derivative plus Laplacian, and then the gradient. So if you plug time derivative plus Laplacian here, and if you plug the gradient here, you get exactly the expression above. So can we use this point of view to design a numerical method? So yes, I'm going to present two methods. The first one is the so-called augmented Lagrangian. I mean, it's based on the augmented Lagrangian, and you have several algorithms. The one I'm going to present in here is the alternating direction method of multipliers, ADMM for short. So let's reformulate the problem. Actually, I think I called it the let's see. I called B the primal problem, and I call this one the dual problem. But anyway, it's just the terminology. So we have this problem A, which is written as the inf of f plus g, as I presented in the previous slide. In general, it would be hard to solve this problem directly because phi is involved here and it's also involved here. So remember that this function lambda is basically taking the partial derivatives of phi. So the idea of the augmented Lagrangian method is if you have a function of, if you want to minimize the function, which is composed of two parts, what you can do is in the second part, you introduce an artificial variable and you make it equal to what you need. So here we introduce an artificial variable q. We say it is it is going to be used for g of q, but separately we impose the constraint that q is equal to lambda of phi. So we go from a non-constrained optimization problem to a constrained optimization problem. Usually the latter is harder to solve. So it's not necessarily a good idea to add some constraints artificially. It may make things harder to solve. But what we do next is we look at the Lagrangian. So this is an adjoint variable, which is going to multiply the constraint. We don't just look at the Lagrangian, we augment it by adding an extra penalty term here, where R is to be chosen. It is a parameter, and it is going to influence the convergence. But for now, I just take it as a constant. So you fix a constant R, and you add this extra penalty. And the penalty is what you want to satisfy the constraint, right? So intuitively, it's going to help to make the Lagrangian even more maybe convex in some sense, because you want lambda phi, you want q to be equal to lambda phi, and this should be true when you really find a saddle point. So you are looking for a saddle point. If you find a saddle point, in particular, it is going to satisfy the constraint, and so this term should be 0. So if this term is 0, it means the augmented Lagrangian is equal to the Lagrangian, at least at the saddle point. So here is, so now the goal is to find a saddle point, okay? And there are different methods to do that. Here is one method, which is called the alternating direction method of multipliers. It's discussed, for example, in the book of Fortin and Blobinski, and it has been used in mean-field games by Benamou and Carlier, and also by Andreev. And then we used it for mean-field control with Ivajdu, and recently in SEMRAX, also with Amal, who is in the audience, and Yuchen Zhu, a former student of NYU Shanghai, who also helped me for some of the codes, and who implemented this ADMM method using a deep learning extension. But here I'm going to present it without deep learning. The idea being that you try to find a saddle point by alternating between the three components. So you have phi, you have q tilde, and you update each of them in turn somehow. So you look at phi and you say phi should be a minimizer of the Lagrangian. If you give me the two other variables, phi should be a minimizer. All right, so I write the minimization problem and I try to solve it. For now, I write it in an abstract way. Then for q, I want q to also minimize the Lagrangian given the other variables. So you see that here I take phi that I just computed and I plug it here, while for phi, I have plugged q tilde and q at the previous iteration. And the last step is to update q tilde. And for q tilde, it's just basically a gradient step. So this is like a gradient step. Okay, so these are the three steps in the ADMM method. And of course, here it's written in a kind of abstract way. And then we need to implement it numerically. I hope here that it makes sense, at least at a high level. In some sense here, in this slide, there is nothing about mean-field game, except the last two comments at the bottom of the slide, but this is a general ADM, so you don't even need to know anything about mean-field games. So somehow, my point is you start from the mean-field game, you have this variational point of view with primal dual problem, and once you have this primal and dual problem, you can use maybe not any technique from the optimization toolbox, but really you can borrow a lot of techniques from optimization and apply them just by changing the notations somehow. So here in this case, let me discuss a little bit the discretization. Again, the Hamiltonian is quadratic, and I want to write a discrete version of the dual problem. This is correct. This is what I call the dual problem. So I will write AH for this problem. And the main point is to use the discrete operators that I introduced before in the finite difference slide. So here I will say C, finite difference section, which was above. It was section number 2. Once you have that, you define discrete operators for F, for calligraphic F and calligraphic G. And you see that the integrals are replaced by discrete sums over time and over space. Okay, here calligraphic G depends on, in fact, a minimization problem. So here KH, in KH is hidden a minimization problem. You see there is a mean over M. So this might be a little bit scary because later on, this would mean that in the ADMM method, we are even going to need to solve a minimization problem inside. So this could be complicated, but for some choices of H tilde 0, at least, then the problem is easy to solve somehow. So you can find the minimizer explicitly. And in that case, you don't need any extra numerical computation for this sub problem. So here I rewrite the ADMM with discretization. So the only difference is you have H everywhere to stress that the operators are discrete. So this is not very interesting. It's just rewriting the previous version. But I want to explain what this means. So what A, B, and C mean numerically. So for A, actually, we want to solve an optimization problem for phi. And remember that now, after discretization, phi is basically a vector in space and time. So you have space discretization, you have time discretization, and so phi is a vector in both time and space. So you can think of it as a matrix, at least if you are only in dimension 1 in space. So we want to compute a vector that solves this minimization problem. If you write the first order optimality condition here, F or C, first order optimality condition, you will find out that the first order condition is in fact a finite difference equation. So here you recover a finite difference equation, which characterizes the optimizer. And then you somehow just need to solve this finite difference equation. For step B, in fact, there is a simplification. So here we have argmin over Q. Again, Q is a vector in space and time, so potentially it's a high-dimensional optimization problem. But in fact, if you look at the definition of G, if you look at the definition of lambda H, etc., you realize that the different points of the grid are not coupled. So what I mean by that is you have your grid here in X and in T. And if you look at the optimization problem, so if you look at, let's say, Q at time N and point I, and you are wondering how it appears, which role it plays in the argmin, well, in fact, it plays a role just by itself. It does not interact with the other points on the grid, which means that you need to solve one optimization problem for each point of the grid. So it's a large number of optimization problems, but it's better than one optimization problem in very high dimension. It's easier to solve. In particular, you can parallelize the computations. So for A, in fact, there are some potential difficulties. So this is a point where I talk a bit about preconditioner, but it's for a different reason. But here, if nu is equal to 0, this one, then it's possible to use a direct solver. And if nu is positive, it's problematic. So the finite difference equation you are going to get here is not the same as the ones we saw before, the AJB and the Kolmogorov-Fokker-Planck equation. It is an equation which involves a B Laplacian somehow, at least when nu is positive. So when nu is positive, the problem is more difficult to solve, and then it's helpful to use a preconditioner. And so here I give some references for that. When nu is equal to 0, then the equation is pretty straightforward to solve. So I am going to show some illustration with nu is equal to 0. And later on, I will come back to this idea of preconditioning with another illustration later on. So here is an example without viscosity. So what I mean by without viscosity is an example where nu is equal to 0 or sigma is equal to 0 in the stochastic interpretation. We take a domain, which is two-dimensional, and in the center you have some obstacle. So this is the domain omega, which is like the unit square, but in the center there is an obstacle. And the mass is going to start here. Let me put maybe a different color. So the mass is going to start in the bottom left corner, and it is going to be attracted to the top right corner. What I mean by attracted is there is a terminal cost, which is small, smaller than in the rest of the domain. The terminal cost is minimal if you are at the top right corner. You can impose boundary conditions. In particular, here we don't want the mass to be able to use periodic boundaries. So you put a constraint so that people cannot cross the walls. And the way you can do that is by changing the Hamiltonian. So here you put a constraint in the definition of the Hamiltonian. The vector xi over which you optimize cannot point towards the exterior of the domain when you are on the boundary. This is the Lagrangian that I consider. So this is very related to the crowd motion example I discussed before. Here, this is going to have the interpretation of making you pay for the velocity. So this was the equivalent of alpha to some power beta star. And then, so what I wrote before, sorry, just to match the notation, I think I said something like m to the power, I think I used gamma and alpha to the power delta. Well, you can put two constants for the exponents. And here for this specific choice of constants, alpha over beta minus 1 and beta star respectively, you find exactly the Hamiltonian described above, which is with power minus alpha and beta. So there is always a game of powers between the Lagrangian and the Hamiltonian. You have to do the computations. But here the Hamiltonian has a simple expression. Notice that here, this means that we take P, or if you want, P is going to be like the control, alpha. So we take P to the power beta, and we divide by m to the power alpha, which means that when you have zero mass, it's problematic. The Hamiltonian is not well defined, right? Or you have to say what happens. So this forces us to work with weak solutions when dealing with the existence theory for mean field games with zero viscosity and with this kind of Hamiltonian. But I will skip the theoretical details, and you are going to see what happens numerically.
Mathieu, there is a question about the viscosity, the meaning of the viscosity here.
Thank you. What represents the viscosity for the game? Yes, good question. So here you can have the interpretation you want about the game. If we think about pedestrians, it means that we have dxt equals alpha t dt. So xt is the location or the position. Alpha t is equal to the velocity, and then that's the evolution. Now, when you add viscosity, this means that you add a term here, sigma dwt, in the dynamics. Now, what is the interpretation? Well, I'm not sure that for pedestrians there is a very good interpretation. Usually we don't work in a stochastic way, maybe in some situations, but usually it's not very common. But we could imagine that when you are in a crowd, so maybe two explanations. One could be when you are in a crowd, maybe you are pushed a little bit by people around you. And another explanation could be that it represents some kind of uncertainty about your position. This is not completely true. I mean, uncertainty about how you control your velocity. Maybe you make some effort to use alpha as a velocity, but in practice, because of some effects, physical effects, you don't have velocity exactly alpha. You have some small perturbation, right? So in real life, I think the viscosity should be very, very small, or maybe even 0. But mathematically, it's usually very convenient to work with viscosity because it makes the solution smoother. All right, thank you for your question. So here we work with 0 viscosity. Here are the definitions. Notice that we have, so I insisted on these terms that I call crowd congestion or congestion effect, because you pay a cost which is proportional to your velocity. And this one is more like the aversion. So why is it an aversion term? Because you have L of xm, it's written just above, sorry. L of xm is equal to some factor times m. And here m is a local dependence. So what appears really in your game, if you write the definition of the game, what appears is m of t and xt in the running cost. And this is equal to some constant times m of t and xt, meaning you pay your cost when m is large at your location, whether you are moving or not. Okay, so I don't always rewrite the interpretation in terms of stochastic differential game, but I encourage you to write always starting from the Hamiltonian, what is the cost, what is the total cost, the dynamics, etc. It's a kind of gymnastic, and at some point you get used to thinking about the correspondence between the PDE system and the game. So this is the initial distribution, concentrated, so you can see on the left, concentrated in one corner, and the terminal cost is minimal in the other corner. And what happens, is that you have the evolution. Again, this is the initial distribution seen from a different angle. So density at time 0 is concentrated on a square, and then the mass moves. Pretty quickly, the mass decreases, and then people start moving forward. So their goal is to move there, right? But you see here there is a bump of mass. So there are some people who are faster, and many people who are slower, and the reason is because of this congestion effect. It's not possible to move everyone forward at the same speed because they don't have the same density, and more density means you pay a higher cost, so you move more slowly. So you see this, and people arrive at the obstacle. So here, maybe we would need a view from above, but here there is an obstacle in the middle. So you see the mass split into 2 parts and goes around the obstacle. And then people keep moving until they reach the terminal state. And you see that the terminal state is very concentrated in this corner. The reason is probably that at terminal times, they don't really pay any cost anymore, so they don't care if the density is very high. They are just happy to have reached the destination. So this is a consequence of the model. You could change the model in order to avoid this peak here and have something maybe more realistic. Or maybe this is realistic, depending on your model. And again, this is based on a setting where nu is equal to 0, so no viscosity at all. So here, if I go back, you see the shape is kind of smooth. So it's not smooth near the obstacle. Here you see there is a sharp boundary because the obstacle is a square, but here the mass is pretty smooth. Here you can see the shape is smooth, but this does not come from diffusion. There is no diffusion in the model. It really comes from the fact that people are spreading because they want to avoid congestion. So you could try maybe an example like this. Imagine you remove the congestion effect completely. Maybe the mass, the initial mass, would move so there would be almost no diffusion, almost no spread of mass, because the agents would move directly towards the target. And here people need to diffuse a little bit because of the congestion effect. So they want to lower the density at their location so that they can move faster. So let me restate that. People who are here, concretely, they pay a very high cost to move compared with people who are here. So people who are here, they can use a very large viscosity, velocity, and they pay a small cost. And people here, they can use only a small velocity, otherwise they would pay a very high cost. In other words, if you use the same velocity vector, you pay a higher cost here than here. All right, further questions on this example? So if not, I will present another algorithm still based on this variational interpretation or variational point of view. So the first one was the alternating direction method of multipliers based on the augmented Lagrangian viewpoint. Second one is primal dual method, which will be based on an algorithm introduced by Chambol and Pock. So let me take one step back and reformulate the problem for a more abstract or more general point of view. Take two convex functions, phi and psi, taking values in R union infinity. So they can potentially take infinite values, which is convenient when you want to impose constraints, basically, like positivity of the mass or terminal cost should be equal, terminal value should be equal to the cost. You can use infinite value to impose such constraints. Take an optimization problem, and you see that here there are two components, phi plus psi, both of them functions of y. So I already explained the augmented Lagrangian idea, which is to somehow introduce an artificial variable to get rid of y here and have an extra constraint separately. But here let's take y in both of them and work with that. Then there is a dual problem, which depends on phi star and psi star in this way. So here, okay. So the first order optimality condition for this problem is the following. So you want minus sigma hat to be in the gradient of phi, and you want y hat to be in the gradient of psi star. Then you can rewrite this in a different way, and in particular using the so-called proximal operator here. So I define it below. In some sense, the proximal operator is a kind of generalization of convex projection. Projection on a convex set, orthogonal projection on a convex set, where you do the argmin. So here it is defined, prox operator for a constant gamma, a function phi, and the input x. And the way it is defined is you take the argmin, so you take the minimizer of phi of y plus some extra term, some extra penalty term, if you want, or regularization term, y minus x squared, and divided by this constant 2 gamma. So what is written above is that you can rewrite the first order optimality condition in terms of this proximal operator. And you see that here we have an expression for y hat and sigma hat. I can say y hat is equal to this, sigma hat is equal to this. So I have found the optimizer, which is a pair y hat and sigma hat for the primal and the dual problem. But not really, I haven't really found the solution. Why? Because in fact, these are equations. These are equations because y hat also appears on the left and sigma hat also appears on the left here. So in fact, I need to solve these equations if I want to find the optimizer. And so there are different methods to do that, but the one proposed with by Chambol and Pock is the following. And there is a proof of convergence, at least when tau and gamma are strictly smaller than 1. I mean, the product is smaller than 1.
Mathieu, there is a question.
Yes, in some sense. So the aim of the regularization term is to make smooth the solution. Yes, in some sense. I think you can say it in this way. And to, yes, and to have a strict convexity. So there are two parameters, tau and gamma. Sorry. Okay, thank you. So there are two parameters, tau and gamma, and when the product is smaller than 1, then there is a proof of convergence. And so this is in the paper of Chambol and Pock. So again, the point of view I'm presenting here is quite general. And the idea is you take your meaningful game, have this variational point of view, and then just do a change of notation to fit in the framework I'm presenting here somehow. So Chambol and Pock's algorithm is the following. Let me just show the full algorithm. So you have 3 steps. You update sigma, you update y, and then you update an auxiliary variable, y bar. And you see that, you see that y bar here is plugged in the equation for sigma. So we don't use y exactly, we use y bar. And here you recognize something that is reminiscent of what I have already described multiple times, which is to use a kind of a damping coefficient to slow down the evolution and to make the iterations smoother in some sense. So how do we update sigma? Well, we solve, so we need to compute the prox. I mean, the prox evaluated at sigma from the previous iteration and y bar, which has already been computed as well. And then you take this sigma, plug it here, you compute another prox, and you get yk plus 1. So, of course, the question is, can we compute these prox efficiently? So what is prox? Let me go back. What is the proximal operator? Let me go back. You see that proximal operator means you need to solve some minimization problem. So in principle, we need to solve a minimization problem at each of these 2 steps. And if phi and y and sigma are vectors in high dimensions, then it can be complicated to solve a minimization problem, right? So it's not clear that the algorithm is always easy to apply, but it turns out that in our situation, the 2 proximal operators are going to be simple to solve. So this is a duality. Okay, I write the dual problem. Okay, dual problem of AH, which so I call the problem B the primal problem before. You can introduce a dual problem. I guess for the sake of time, I will skip the details. I just want to show that you get a discrete equation. And so in the end, you can rephrase the meaningful gain problem as this optimization problem. So this is the discrete primal problem, in fact. So here I should say primal to be consistent with my terminology in the previous slides, which was the problem of inf over m and w of calligraphic B of m and w. You remember this is where I started with for this variational approach. And so I'm saying this problem is approximated by the following one, where now M and W are vectors in time and space. So this is an optimization problem, and you are going to get a function phi and a function psi of M and W. So MW plays the role of Y in my presentation earlier, and you can use, for example, this primal dual algorithm of Chambol and Pock. And you can use several other algorithms. So I give the reference later, but in the, or maybe I gave it already in this paper of Briceño Arias and Francisco Silva and Dante Calice. There are several other algorithms based on the same intuition of primal dual problems that are described. Okay, so let me skip the complete description. Just I want to mention that this here function psi is given as the indicator function, and this can take infinite value once a constraint is not satisfied. So we are really in this framework that I discussed before with the primal and the dual problem with functions phi and psi taking values in R union infinity. So if you implement this method, here I'm borrowing this plot from a follow-up paper, but you have similar experiments in the static case, the stationary case in the original paper, and here we did it also during some racks in the dynamic case. So in this dynamic case, you have the initial distribution, which is uniform over the torus in dimension 2. So you have x1 and x2, the 2 dimensions of space, the value of the density. So here it's constant equal to 1. And then the distribution changes because of the running cost. So at time t, for example, 0.1, it takes this shape, t equals 0.5. So you should read it like this, then like this, then like this. And at terminal time, it has some shape. Here, I just write the running cost. So F, the terminal cost is 0, and F is something like M squared, meaning you pay a cost which is not just M, but even quadratic in M for the density at your location. So you want to avoid the crowd, but you have some preferences in terms of space. Here, there is no interpretation for this cost, but you see it's a trigonometric, a sum of trigonometric functions. And so there are some points where the sine is minimal or the cosine is minimal. So basically you look at h bar. H bar has some local minima, and these local minima, so there is a minus sign here. So the local maxima of h bar are going to be local minima for f, so running cost f, and they are going to attract people to these locations, which is why we have concentration of a little bit more mass here and here than in other places. What else? Yes, okay, there are more details in the paper, so you can check this. One thing that we did, one experiment we did in this one, is to look again at this turnpike phenomenon. So it's described from the theoretical point of view, in particular in this paper of Porretta and Zuazua, if you want to take a look. And the idea is, so in the first paper here, the authors solved the stationary case, and in the second paper, we adapted the method for the time-dependent problem. So what you can do is you can compare the two solutions. So you can measure the distance between the M stationary for the stationary mean field game, or the long time if you want a mean field game. So the PDE system is independent of time. And you can look at M at time t, where M is the solution of the the time-dependent problem. And what you see when you look at this norm is that at the beginning, the value is pretty large because m has an initial m0. So here, this is at time 0, m is equal to m0. So you have no choice, and it's different from the stationary m. But as time goes by, the distance decreases, and here it's almost 0, meaning that towards the middle of the time horizon, or the middle of the time interval, the solution is basically stationary. So in other words, between, let's say, 0.4 and 1.6, almost nothing happens. The behavior is just stationary. And then you could just shortcut this part by solving the stationary problem and plugging this as part of your solution. So what really matters is what happens here and here. So this turnpike phenomenon is, I mean, it's an interesting feature. I think it happens in quite a few situations. It's not a general phenomenon. So there are meaningful games for which it's not true. There is no turnpike phenomenon, and you just the solution keeps evolving. For example, you could have some oscillatory behavior where the mass keeps moving around forever, and there is nothing stationary. So it's not a general phenomenon. All right, so we have some time for to describe the probability, I mean, methods based on the probabilistic approach. I will be much faster on this. So even though we have less time, I think it's fine because I have fewer things to say. But I want to say that there are some methods that exist also for the probabilistic approach. So I will start with a Picard scheme developed by Francois and co-authors, and then for making class of FBSDs, and then some approaches for mean-field control problem in special situations where the dependence on the distribution is only through moments and a finite number of moments. So be beyond the linear quadratic case, but not a full dependence on the distribution, or not a general dependence. So here is a Makin-Vlasov forward-backward SD system. Again, you can check the end of lecture 1. During the first lecture, at the end, I went a bit quickly on this part, but you can check how to derive such FPSD systems, or you can check the book of Francois and René Carmona. But in mean-field game and mean-field control, typically we obtain such systems when we use a probabilistic approach. X is a state of one agent, and Y is either the value function or the derivative of the value function. So the idea of the Picard scheme is to solve the forward and the backward equation iteratively. So imagine that you are given YZ as well as the law of X, then you can solve for X. And once you have X, you can compute the law of X. And then given X and the law of X, you can solve for Y and Z. And then you can repeat and go back to here. Okay, so this is the idea. You see that there are more components than in the PDE approach, but it is basically the same idea to solve the forward and the backward. So here, the presentation is based on a paper by Jean-François Chassagneux, François Delarue, and Dan Crisan, and then a work also during SMRX by Andrea and Julie and the same authors and co-authors. So here is a Picard scheme. Intuitively, it's just what I described before. Given the law of X and Y and Z, you can solve X, and then you solve the backward equation.
Mathieu, there is one question about the meaning of this. Mathieu, sorry.
Yes.
Yes, thank you.
Thank you very much. So yes, so there is a question which is about the role of alpha in this FBSD system. And so thank you, you are right. Alpha does not appear in this FBSD system. And the reason is that I already replaced. So you see that here I'm using the notation capital B. So capital B of X, M, Y, and Z would be the little b, except that little b should be a function of x, alpha, and m. So what happens? What happens is, in fact, that alpha has an expression in terms of x, y, and z. And so I already replace. So I need to find this alpha hat. It's not possible for all costs, etc. But alpha hat is a minimizer of the Hamiltonian.
Mathieu, there is another question about the meaning of z.
Yes, thank you. And the meaning of z. So here, so I can answer that z is here to make y adaptive, but I don't know if this helps. So the idea is that you need an extra term here to make y adaptive. And the meaning, so intuitively, maybe this would be more helpful. So if y is equal to u of t and xt, z is equal typically to the gradient of u and t and xt up to maybe a factor sigma, but that's basically the derivative. So you can see that really by doing the derivative. So here I will refer to the lecture 1 if you want at the end of the slides, and otherwise the book of Carmona and Delarue. So you have about 1,500 pages to see that in detail, in case you want to understand everything about Z and these forward-backward systems. But if you want more details, I'm happy to give more details later. And for now, I will, so this is the algorithm. And basically, it relies on this function phi. And well, as we have seen before, this function phi, maybe it has a fixed point, maybe not. If it does not have a fixed point, then well, the algorithm is not going to converge. Or rather, if it is a strict contraction, then you are sure that the algorithm is going to converge. Otherwise, it is not clear. So what the authors did is to use a small time horizon and then try to decompose the problem into problems over shorter time horizons. And intuitively, if you split the problem into sub-problems with a very small time horizon, maybe these PCAR iterations are going to converge on each sub-interval, and then you paste together the time intervals, and you get a solution for the global time interval. All right, so here I explain a little bit the detail, but Francois knows that much better than me. And anyway, there is not much time. So basically, the scheme is a little bit more complicated. Let me show the algorithm. So this is what I call the global solver. So you see that inside, we call the solver solver here, which is for the time horizon starting at tm+1. So here you decompose t0 until t nt, let's say the last one, capital T, t0, t1, etc., until capital T, and you try to solve on each sub-interval by calling recursively the solver.
Mathieu, precisely, there is one question about what happens when t is small.
Okay. Is there a reference? Yes, okay, thank you. So the question is about why we have a contraction for small t, and is there a reference? So yes, I can provide some references. So it's a good question, thank you. If I go back what I claimed here, it's very intuitive. So let me put that between quotes. But I think I gave one intuitive explanation yesterday. The idea is basically if the time is very, very small, the solution does not have time to change too much somehow. So not much is going to happen. And then you typically have a strict contraction. Another way to say it is you look at this function phi, you check the condition to be a strict contraction, and you will realize that this condition will involve a constant, which should be smaller than 1. And this constant depends on time. And typically this constant goes to 0 when time goes to 0. So if you take time small enough, then the constant is smaller than 1 for sure. It's more complicated than that, but intuitively, you really take this function phi, write the condition to be a strict contraction. Now, for some references, I think there is the original paper of Keynes, Huang, and Malamé, which already used this technique. And then it has been used in several works after that. So if you want to send me an email, maybe that would be simpler. I can send some references. Okay, so here, this is the algorithm, and it relies on calling recursively the solver. Now, there is one thing that we need to discuss, which is how to implement concretely this, because we need to do something about space. In particular, you see here there is a law of X involved, and the question is how do we represent the law of X? If X takes continuous values in R, what is the law of X and how do we approximate it? So one way can be to use a binary tree approximation, and then at each time step, you have a number of possibilities, possible realization of X, and you can compute the probabilities of these realizations. And another one is to use a grid. So in the first case, you start from X0, and then you have two possible locations, etc. So you see that you have possibly exponentially many locations after in terms of number of time steps, whereas in the other case, you have a grid in time and space. So here, this is time and this is X, for example, and you compute the value of the distribution at these points in the grid. For the sake of time, I'm probably going to skip the details, but you can check. So in particular, in this paper, you have more details and you have numerical experiments. I didn't want to steal the figures from other people's work, but there are some very nice experiments also in these papers. And so here, this is the time discretization with the tree-based method. And this is, okay, just one slide of remark. You can compute the law by taking a weighted sum. So you have possible locations, which are the points given by the tree, and you take a weighted version of that, and this gives an approximation of the law of X. And you also need to compute the conditional expectation, and this can also be computed using the tree. However, if you have NT steps, you have 2 to the NT possible paths at terminal time. You have 2 to the NT points. So this is tremendous if you have many points in time. Sorry, I think there is. Okay, thank you. So there is another question. What is the cost of time for this algorithm? That's a good point. I am not so sure. So there is the algorithm here, and then there is the implementation using the tree. Here there is already, okay, so I think it should be possible to compute it. Okay, I don't know the exact answer, but what you need to be careful about if you want to estimate the complexity is that this is a recursive algorithm. So when you are at time 0, you are going to call the solver for the next time step, which is going to call the solver for the following time step, etc. So there is some computational time for this, and then you need a number of iterations for convergence of Picard. So then it depends on the threshold that you want, and I'm not sure, but typically Picard is going to converge very quickly. It needs just a few iterations. As we saw yesterday in the linear quadratic case, just in maybe 10 iterations, you already get a very precise iteration, a very precise solution. All right, this was about the computation. Then there is a memory cost, and this, I believe, depends whether you use the tree-based approach or the other approach, which is based on a grid and which has a fixed cost somehow in space. Thank you. All right, so yes, this is a description, and I went a bit quickly, but this expectation here is a conditional expectation. So the reason I mentioned that is because it is going to be a problem also in the next method, conditional expectation. And so in general, it's not easy to estimate a conditional expectation. So this is a conditional expectation of y at time ti plus 1 given the current time step, which is ti. And you want to compute this conditional expectation. So if you have a binary tree, it is possible to compute it using a weighted average using the following time step. But in general, it can be difficult. So here, using this tree-based approach, it can be completely implemented. And yes, so I believe the idea behind using the grid was maybe there are some recombinations. So intuitively, when you are here, you have two possibilities, and then two possibilities again, etc. But maybe these two are actually pretty close. So maybe you don't need really 2 points. So here you are going to have two different points here in your tree. But in practice, maybe these 2 points, if you think in terms of location, maybe they are close, and then you can merge them. But merging a posteriori is difficult. So maybe what you can do is, instead of using a tree, using a grid where the discretization of space is fixed in advance. So, well, okay, actually there is still some cost, but that's one motivation. So what I can do in the last few minutes is just to finish explaining this algorithm, and then I will stop before the next algorithm, so we have some time for questions. And then this afternoon we restart, and in fact this will be a good transition towards what we will discuss this afternoon. So this algorithm, this implementation using a grid relies on the idea that, in fact, y. So previously, you remember, I said that following a question that we had, I said yt is equal to u of t and xt, but you can also add the law of xt here. In fact, the law of xt is going to be deterministic, so I don't really need to plug it. It's enough to know what time it is. But in some cases, you want to make the dependence on the distribution completely explicit. And here, z is equal to v, and in fact, v is the gradient of the value function. But we don't know these functions. We don't know u and we don't know v, right? So the goal is to compute u and to compute v. So one idea is to start with some guess, or to imagine that you have already computed u and v at the next time step, uk plus 1 and vk plus 1 for some time step. So here is the scheme. So remember, you want to solve the forward equation, and then you want to solve the backward equation, right? But the forward equation involves the distribution. So this plays the role of the law of x. U here plays the role of y, and v plays the role of z. But you assume you have this function from the previous iteration, and they are given to you. So actually, yes, okay. Well, here I do it with index k, so it's really given to you from the previous iteration. So now we discretize space and we discretize time. So we have a grid gamma in space as well, whereas before, using the tree-based approximation, we had only a grid in time. For the law, we are going to force somehow the distribution to stay on the grid. So basically, the distribution is going to be approximated by a histogram on the points of the grid. So it will be a vector of weights. And if the process goes outside of the grid, you can project. So let me go back here. You have this evolution. This, even if you discretize time, xt plus 1 might end up outside of the grid. So you project to have really a point on the grid. And in this case, you can write a discrete time and discrete space evolution. So here, this is the candidate for x ti plus 1, but this candidate might be outside of the grid, so you project. And now the question is, well, what is the distribution of that? What is the distribution over states for this x? And it is something that you can express using a transition kernel, and you can get an expression of mu at time ti plus 1. At least, well, at least for reasonable b in the examples. The second step is to look at the backward equation. And for this backward equation, so we want to compute the function here, u, and the function is given by a conditional expectation here again. So the reason why I stress the conditional expectation is because computing conditional expectations is difficult, and that's one of the motivation behind the deep learning methods I will start presenting this afternoon, which kind of circumvent this problem, and we don't need to compute conditional expectations, at least not explicitly in the same way as we are doing here. So forward equation, this is a summary. Forward equation, you can get mu k plus 1 using the transition of xk, and you can get the backward equation by solving this part. So yes, details and numerical examples in this paper. So I think I will skip this method. I will do it this afternoon. Maybe let me just jump to the conclusion. What we did here this morning, I know it was pretty dense, a lot of information, at least from my point of view. I think it's a lot. So there was two numerical schemes for forward-backward PDEs, one based on finite differences, one based on semi-Lagrangian scheme. Optimization method, so this primal dual point of view, here again with two methods, and two methods using the probabilistic approach. The second one I haven't discussed. I will do it this afternoon briefly. I want to mention that there are other methods, for example, gradient descent-based methods, monotone operators, in particular by Diogo Gomes and collaborators, policy iteration, recently by Cacace and Fabio Cagnili and co-authors, including Tong, who is a collaborator, and finite elements instead of finite differences, cubator method, and so on and so on. So there are other algorithms, other numerical schemes, other algorithms around. I try to focus on some of the maybe most common one, or at least to provide the main ideas. But feel free to let me know if you're interested in some details over other methods. All right, and the motivation for this afternoon is that these methods are typically, they work very well, they can be analyzed, well understood, we have all the background of numerical analysis, but typically they are restricted to small dimension and relatively simple structure of mini-field games. And so this is a motivation to develop numerical methods based on machine learning. I will stop here and thank you for your attention. If you have questions.
Thank you a lot, Mathieu. This is a wonderful job. I think that this is a lot of work for you, and this is really very useful. I guess that also the lectures online, so on YouTube, will be very useful for even for people who didn't attend your lectures today. Are there any questions online?
Okay, I think we are a bit tight on time anyway, so I can also answer questions later. You can contact me anytime or this afternoon if you have further questions.
Yes, we can do this. You had some questions today during the the lectures, so you have many thanks on the chat.
Thank you.
Yeah. Yes. Okay. Thank you again. So we can resume at. So once again, this is 2:30 in France, 1:30 in Morocco. So in 1 hour and a half. Abdou, is there anything else you would like to say, or this is enough? Should I say something else?
I think you said it all. So just thank you, and maybe stop the broadcast.